Hello everyone, welcome back to Electronics 1, or Lecture 7 today. So following up from last class, we were talking about op-amps and talking about op-amps in an ideal nature, and we concluded that an ideal op-amp is basically an ideal voltage amplifier, just like we looked at with the amplifier models earlier in the term. Infinite input impedance, zero output or infinite input resistance, zero output resistance. So a couple of the main properties of a voltage amplifier. But we also introduced a couple other properties that are characteristic of an ideal op-amp, and of course op-amps aren't quite ideal, but op-amp is pretty close, and our ideal approximations allow us to make pretty near calculations when using those approximations for op-amp circuits. So just to take another figure from the textbook. So these are both from Cedar Smith, and here we see some of the other properties of an ideal op-amps already listed in infinite input. We're actually listing it as impedance, but we've been just talking about it as a resistance for now. Zero output impedance, zero common mode gain. So we talked a bit about how an op-amp, because it is amplifying the difference between the inverting and non-inverting input, that any signal that's common to both inputs, or is the common mode signal, will be eliminated from the output. We also refer to that as common mode rejection. We'll talk a bit about that a little bit later on. We also talked about it having infinite open loop gain, so that term A in the gain term of our voltage amplifier, we said for an ideal op-amp is we consider to be infinite. Allows us to assume that the voltage at both inputs is equal. We'll see that's very beneficial when we do our circuit analysis. And the fifth property is that an ideal op-amp has infinite bandwidth. What that means is there will be no attenuation of frequencies of any magnitude. Okay, we won't deal with that too much or at all in this class. We kind of leave the frequency aspect out of this course, but those of you that continue on to Electronics 2 will see the implications of bandwidth of your op-amp. Okay, so I ended the last class talking about the fact that our open loop gain is, well, again, we say it's ideally infinite. It's not infinite, of course. We said it is typically in the range of 100,000 to 1,000,000 volts per volt, and that value can be highly variable. Okay, so that's not ideal if we're trying to build a system that's provides a fixed gain. So we want to have control over the gain. Right, makes sense. We want to be able to control precisely how much gain an amplifier is exhibiting. Right, when you want to be able to precisely control the volume of your stereo, for example, if we're talking about amplifiers. Okay, so in order to set this gain of an op-amp, we use what's known as negative feedback. So for an amplifier that's implemented using an op amp, we have to use negative feedback to control and stabilize the gain. Okay, so what's negative feedback? So negative feedback is a technique where part of the output signal is fed back, hence the name, to the input, and that feedback is used to subtract from the input, hence the negative aspect of the feedback. Okay. So again, it's this subtraction aspect that makes the feedback negative. We can have positive feedback is a form of feedback. Positive feedback in an op amp would generally cause it to become unstable and oscillate, and there are applications to do that if we're trying to generate an oscillator, and that's something that is also explored in electronics too. Okay, so let's look at an example of an op amp with negative feedback. So I draw my op amp. So here's my typical op amp symbol with a plus labeled on the non-inverting terminal, a negative labeled on the inverting terminal. But I'm now going to use a voltage divider on the output. Okay, so let me label this as output, and I'm going to actually apply my signal here at this input only, and the non-inverting terminal. But I'm going to take a portion of this output signal, and I'm going to use a voltage divider to again just grab a portion of this signal and apply it back to the inverting input. Okay, so the fact that it's applied to the inverting input means we know that the output the output signal, right, remember that the output is equal to the gain times the differential signal, where VD is equal to the difference between the inverting and the non-inverting and inverting terminal. So this is why that feedback is negative, because we're applying it to the inverting terminal, which is going to subtract from the input that's applied to the non-inverting terminal. Okay, so again, we let me label these resistors. Let's call this R1 and R2, and let's put some additional labels on here. Okay, so here at this point, we're applying voltage divider to feedback just a portion of the output signal. Okay, so guess technically it's the combination of these resistors that's the voltage divider. So only the voltage at this point here is actually fed back to the input. Let's call that voltage at this point VA. Let's put some other voltages on here as well. Let's call this let's call this voltage the voltage at the positive terminal, the voltage here at sorry, not the positive terminal, at the non-inverting terminal. This voltage is the voltage at the inverting terminal. I'm also going to label my currents here, right? The current flowing into this non-inverting terminal, again, assuming infinite input resistance, this will be 0. The current flowing into this terminal, the inverting terminal, will also be 0 if we're assuming infinite input resistance. So that means that the current flowing out here, right, that's all the same current here along this line, so that current is going to be 0. So we can apply a simple voltage divider equation at this point VA to calculate the voltage at VA. Let's talk about another aspect of the op-amp that is going to be very helpful in analyzing this circuit. We said because we assume infinite open loop gain, so maybe I'll just write that down here. So assuming AOL is infinite, and again we won't actually state this every time. I just want to remind you that this is the reason that we say that the voltage at the non-inverting terminal is equal to the voltage at the inverting terminal. So if that's true, well, we see that the voltage at the input is the voltage at the inverting terminal, non-inverting terminal. We're saying that that voltage is equal to the voltage at the inverting terminal, and that is also the voltage that is at the center of our voltage divider here, right? So the voltage, this is also equal to the voltage VA, because that voltage VA appears is going to be that same voltage everywhere along this conductor, right? Because there's no circuit element in between there. Okay, so really what we want to get to here is the point where we say, well, the input voltage is equal to the voltage that's at the center point of that voltage divider between R1 and R2. Okay, so let's again say that the input voltage is equal to the voltage at VA. The voltage VA can be calculated as the resistor R1 over R1 plus R2 times the voltage that's applied to the top of that voltage divider, which is the output voltage. Okay. So we know that, well, let me just rewrite this. So we're saying that the input voltage is equal to R1 over R1 plus R2 times V out. We know that gain is equal to, from looking at our amplifier models, gain is equal to our output voltage divided by our input voltage, voltage gain in this case. So rearranging that formula above, pulling V in over to this side and pulling this term over to the other side and dividing it, we get a V out over V in, which is equal to R1 over R1 plus R2 over R1. Okay, just clean that up here. And so that's just manipulating that equation. Manipulating that equation a little bit further, I can put the two terms in the numerator, split those up over a denominator that's R1. So if I break this equation up like this, so that's still equivalent to the equation above, we get an equation for my voltage gain as 1 plus R2 over R1. Okay, this gain, which is the gain of this amplifier configuration, and maybe I'll redraw it down here. I'm going to draw it a little bit differently, just so you can recognize it when you see it drawn this way. It's quite common to draw this circuit this way. Okay, so that's the same circuit. I've just moved that point VA over to here. Okay, that equation that we found is what's known as the closed loop gain of this circuit on the right. And we'll notice that this is in fact a non-inverting amplifier. What do I mean by that? I mean that the gain is positive. Okay, the signal, whatever signal is applied to the input, will have the same phase, if you want to think about it that way, or it will be going positive at the same time as the output is going positive, right? So if I put in this small signal here and I observe what the output was, and the output is going to be bigger if it's amplified. It's going to be bigger as a function of that resistor ratio. I should label my resistors here, R2 and R1. But again, it will be in phase, right? This is going positive at the same time this is going positive. This is going negative at the same time this is going negative. Right. Just let me fix this here, I guess, just to try to make my scale the same. So smaller signal, but okay, so again, this is positive at the same time as the output's positive. Okay, so that's a non-inverting amplifier. Let's look at a slightly different configuration. And again, this is a very characteristic circuit and equation for a non-inverting op-amp amplifier. This is a very common circuit to use. Just a warning, sometimes, often in fact, this resistor R2 is referred to as RF, the feedback resistor, and in which case the gain would instead be 1 plus RF over R1. Right? It's the same thing, just replacing R2 with RF. Just it's really common to refer to that resistor that's connected directly between the output and the input as the feedback resistor. Okay, let's look at a different configuration of an op-amp amplifier with negative feedback. I'm going to flip my drawing now, and I'm going to show the inverting terminal on the top. Okay, and we have the luxury of a op amp. It's kind of a symmetrical figure. We have the luxury of placing the inverting terminal on the top, or the non-inverting terminal, just based on what's convenient for the circuit you're trying to show. Okay, and again, I want to apply some negative feedback, so I'm going to make a connection between the output and the input, and it has to be going back to the inverting terminal in order for that feedback to be negative. So here I have an output signal, but now I'm going to apply the input signal through a resistor. Okay, so my input signal is here, and that's going to be applied through this resistor R1, and I have this resistor R2 in the feedback path, and I'm going to tie the non-inverting terminal to ground. Okay, let's do some analysis on this circuit to see if we can come up with a gain expression for this equation as well. First thing I want you to note is the voltage at this non-inverting terminal is 0 because we have it tied to ground, and because of the ideal assumptions we make about an op amp and its infinite gain. We say that, right? We say that the voltage at the inverting terminal is going to be equal to the voltage at the non-inverting terminal. We're always going to do this when we do op amp circuit analysis. Well, that allows us to say that the voltage at the inverting terminal is also 0. Okay, this here is what we refer to as a virtual ground. Why? Well, because the voltage at this point here, maybe I should even go right to this point when I specify it. The voltage at that point, although it's not directly connected to ground, the voltage at that point is 0. Okay, so that's an interesting discovery. Let's label. We know that the current flowing into this in non-inverting terminal 0. The current flowing into the inverting terminal is also 0 because of our infinite input resistance. Okay, so let me label a couple of other currents on here. Let's label the current through resistor R1 as IR1, and let me show the current through R2 as IR2. Okay, and let me go one step further and label the voltage drops across these resistors. Let's call this voltage drop VR1, and let's call this voltage drop VR2. Okay, so those voltage drops are going to be a function of the current flowing through those resistors. So the voltage drop VR1 is going to be equal to the current through R1 times the resistance R1. Okay, the same can be said about VR2. The voltage drop across resistor R2 is going to be equal to the current through R2 times the resistance R2. Okay, now you might note that this resistance VR1 here, well, that resistance is equal to the input, the voltage VR1 is equal to the input voltage VI. Why? Well, because the fact that this point at the inverting terminal here is 0, so this voltage VI is the voltage at the input with respect to ground. So that is that VI is the voltage across R1 again, because again this point is ground, so VI is a voltage with respect to ground. That same voltage appears across R1, so we can, rather than call this VR1, we can call this the input voltage, because they're equal. Okay, so this is equal to the input voltage. We can make a similar argument on the output. If I look at this voltage V out here, that voltage is a voltage with respect to ground. Okay, so that voltage with respect to ground, and I have my virtual ground here over at the inverting terminal, I can think about, well, V out is really this voltage at the output with respect to the virtual ground or the inverting input terminal, right? So that is my voltage V out. That we see is equal to the negative of VR2. It's just that voltage across to R2, but in the negative sense. Okay, so I can call VR2 here is simply equal to the negative of V out. Oops, sorry. Okay, again, this is just because I know that negative V out is equal to VR2. They're both the voltage across to R2. One's just has the opposite sign to the other. Okay, so let's make another observation here. I'm kind of making a mess of this diagram. Let me clean this up a little bit. Maybe I'll take these arrows as well. Let me take these other voltages out here as well. We've already kind of dealt with them. What I want to focus on now for a minute is the current at this inverting terminal, right? So I have the current IR1 flowing in here. I have current here, I inverting is 0, and I have a current that's flowing up through here that's equal to IR2. So applying KCL at this point, at this node, I know that the current into that node must be equal to the current out, and there's no current out in the input, right? So there's no current flowing in here. So that means that IR1 must be equal to IR2. Okay. So I can make a statement here that says IR1 is equal to IR2, because again there's no other path for that current to flow because it won't flow into the input. So let me just give that the current a generic name. Let's just call it I. Okay, and I'm going to substitute that value of I into both of these equations here. Okay, so now I have an equation that says the input voltage is equal to that current I times R1. The negative of the output voltage is equal to that current I times R2. Okay, doing some rearranging here, I can say that I is equal to input voltage divided by R1, or looking at it from the output perspective, I can say that current is equal to the negative of the output voltage divided by R2. Okay, both of these terms are equal to I, so I can set them equal to each other. So VI over R1 is must be equal to the negative of V out over R2. Again, I know that voltage gain is defined as the output voltage over the input voltage. So rearranging that equation, I get an expression that says the gain is equal to the negative of R2 over R1. Okay, so just let me redraw the circuit again, because it's a very characteristic op-amp amplifier configuration. Okay, so this is R1, this is R2. Again, sometimes this is referred to as RF, in which case my equation for gain would be equal to minus RF over R1. Okay. So again, the closed loop gain here for this configuration of op-amp amplifier, closed loop gain, is a very simple expression that's purely based on the resistors, just like it was up here. The big difference here is this negative sign that implies that the gain is negative. So this is what's known as an inverting amplifier. Okay, so those are two very common configurations of op-amp amplifiers. You will use them going forward in this class, and probably many applications in the future quite extensively. The near ideal nature of an op-amp makes for a very nice device for interacting with, because the behavior is very close to ideal, and these gains are very close to being completely independent of the actual gain of the op-amp itself. So you might find that interesting, in that nowhere in this expression is that open loop gain term that we said was 100,000 or a million, purely based on your resistors in that feedback network, which gives you the capability to very easily and accurately control the gain of an op-amp. Next class we'll look at some different configurations of op-amps for some other applications besides just pure inverting or non-inverting amplification.